Today I'm going to talk really quickly in a sort of crash course about annealing and some casting stuff. But before I start, I want to thank a few people. That's really important. To acknowledge those people that I learned a lot of this information from, and I've made some of my own sort of judgments based on some of the things they taught me. Dan Clayman, who taught an amazing casting workshop that talked a lot about annealing and mold making and whatever when I took it with him years ago. Henry Halem, who wrote the book on glass blowing, literally Glass Notes, and talked a lot in there about some of the basic principles of annealing and did a lot of the revolutionary foundational work for glass casting and mold making that really got us to where we are right now as a studio glass community. I want to thank Bullseye Glass out there for a lot of the things that they've made public, their research that they've made public on the sort of the practical science of annealing and casting glass. And my old art professor, Sean Mercer, who got me to think about this stuff. And also the person who gave me my first real lesson on annealing, Steve Dureau, who currently runs Salisbury's glass department in Salisbury, Maryland. Okay, thanks over. Let's do this as fast as possible. What is glass annealing? Really simply, it's this: controlled cooling from working temperature down to room temperature. Simple as that. Pretend I made this cup in the hot shop, and when I was working it was 2,000 degrees, and when I finished making it, it's 1,000. Suppose I set it down on a table in the hot shop. Well, the table that it's sitting on and everything else is 90 degrees or something, and that cup is 1,000 degrees. That's 900 degrees difference. But more importantly, that's 900 degrees in size difference, because like almost every other material, glass expands when it's heated and shrinks and contracts when it's cooled. So this cup was 1,000 degrees. The inside is trying to be 1,000 degrees size, and the outside is trying to be room temperature size. Those are vastly different. So imagine what's happening. The outside is shrinking, pulling in on itself, but the inside is bigger, so it's cracking apart and it slowly pulls itself apart. Or another way to think about it, a better way to think about it actually, the inside is trying to be bigger than the outside, and so it blows itself apart. And anybody who's been in a hot shop for any length of time has heard glass explode like that and knows exactly what I'm talking about. That is the sound of glass self-destructing when it's cooled in an uncontrolled manner. So what is glass annealing? Simply cooling glass in a controlled manner. We've got to get the inside and the outside, the surface and the core, to cool at roughly the same temperature all the way down from working temperature to room temperature. Pretty simple. So let's talk about some terms that allow us to understand and do that. So the first term here is the annealing point. The annealing point is really simply defined. I'm not going to define things with numbers necessarily because every glass is different, but for our purposes, we're talking about system 96. 960 degrees is the understood annealing point. Above that, glass will begin to move. So annealing point is simple. It's the point, the temperature above which glass begins to move. Not melt, by the way, just soften and bend so that it can be deformed by gravity or force. The other really important, and this is probably the most important one, is the strain point. The way I understand it is this: the strain point is a point below which, the temperature below which, no permanent stress or strain can be added or removed from a glass body. It's a point, the temperature below which you cannot do that. So let's take my cup again. So pretend that I wasn't an idiot and I didn't set this out on the table. I made this cup like I did, and I put it in an annealer, and it cooled down in a controlled fashion. When I took it out, what if the first thing I did with it was I poured boiling hot coffee into it? What would happen? We know that things expand when they're heated, so the thin part of the glass would expand much quicker than the thick part because it would heat up faster because it has less mass, so it would absorb that temperature faster. It would expand, so this ring would expand, and it might crack from this ring down. It might blow up actually. But if it didn't, and it lived through that process, and I was able to drink my coffee from there, when this was back to room temperature, there would be no permanent strain or damage done to this cup because all that happened way below the strain point, which is typically speaking in a soda lime glass, somewhere above 750 degrees. And specifically for spectrum glass, system 96, roughly 890 degrees Fahrenheit, plus or minus 10 degrees. So those are the two really important things. Annealing happens between those 2 points. Annealing happens somewhere between the annealing point and the strain point. So we're going to talk about this chart over here, and we're going to get back to some of those things. But first, let's jump tracks a little bit here and talk about casting and some of the issues with that. So the way I learned to program a kiln was to do it for casting, was to do it in 2 separate stages. The first stage is the mold curing and the casting program. A whole separate program over here is the annealing program. So let's talk about what's going on here and introduce a few other little concepts if I can really quickly. So the first, mold curing. I just need to get my mold up to temperature without cracking it. I need to dry it out, and I need to do it in a way that doesn't crack it. So that means it needs to be done in a fairly slow and even. Imagine annealing glass, but the opposite. I'm trying to slowly heat this mold up in an even way so that the inside and the outside of the mold all heat and expand at the same rate and dry out at the same rate. Once I get up here and I'm at 1,000 degrees, I'm going to go ahead and jump up to my processing or my working temperature. If it's a casting, say 1,500 degrees Fahrenheit. In the old days, they would just spike it as fast as possible. You see that in a lot of old program charts, as fast as possible up to temperature. Well, they were doing that because they wanted to avoid what's called the Devitrification Range, which brings me to this term here, point of liquidity. That's the point, the temperature, where above that, glass turns from a solid to a liquid. So between the annealing point and the point of liquidity, the annealing point is lower than the point of liquidity. For our purposes, annealing point 960, point of liquidity 13 something, 1320 something, 1350 something. That's where the glass starts just being bendy and starts to become a liquid and ball up on itself. The surface tension is broken and it wants to pull in and be that magic 6 millimeter thickness. That's also critically the point where glass wants to devitrify. So what's devitrify? When you take raw silica, soda, lime to make soda lime glass, you melt it. You take crystalline silica, and through the process of heat and other things, I'm not a chemist, you turn that crystalline silica into amorphous silica. Glass is an amorphous solid, not a crystalline solid. If you devitrify glass, vitrification just means to glass something, to turn something into glass, to melt it. If you devitrify it, it turns it back into those crystalline materials. You're taking the material that makes up glass and turning it back into its constituent parts in a way. Again, I'm not a chemist. I'm sure there's a bunch of people out there online that are going to be like, what are you saying? But for our practical purposes, that's true. The glass turns back into crystalline form. We want to avoid that because devitrification is like a cancer, and it will eat through an entire body of glass and eventually destroy the whole thing unless it is excised, literally cut out of that body of glass. So we know that that happens around 13 something, but we also know that there's a new notion, a thing called quartz inversion, which apparently metal casters have known about for quite some time. If you're using any kind of silica-based mold refractory material, it goes through quartz inversion at roughly 1150 something Fahrenheit. So when it does that, it's the crystal, the silica suddenly expands. And if all of it doesn't do that at the same time, then what you'll get is fractures in weak spots in the mold. You might not see them, but when that mold gets up to temperature and it's sitting at casting temperature for hours and hours and hours, it'll fracture, maybe you have a mold failure, or at the very least you'll have mold flashing. So we need to go very slowly through that temperature, and then we can spike through the devitrification range up to processing temperature. So that's casting. Let's get back to annealing now. On the other side, we still have to think about devitrification on the way down. So the first step is a devit crash. Still thinking about the point of liquidity in that range. I'm going to crash from the working temperature 1500 down to 1250 or so. Why not all the way down to 960 to annealing temperature? Well, a couple of reasons. First is, if it's a closed mold that is surrounding an object, I need to think about shrinkage. If that mold is insulating that glass, the surface of it would freeze because I crashed the kiln and it's getting really cold. The surface might freeze, but the interior stays hot. And it still has to shrink, but it can't pull from the top because the top's frozen. So it's gonna suck in, and you get suckers. You get shrinkage. That happens specifically because you cool down too quickly from your working temperature to your annealing temperature. But of course you need to skip the devitrification range because you don't want to devitrify your glass. So what do? We cool down to 1250 through the devit range. We don't have to worry about that anymore. We're now at the 1250 range. And then we move very slowly down to the annealing point. And for us, at least the way I teach it, the annealing point is not the set annealing point of 960. Remember, the annealing can happen anywhere within the range between the annealing point and the strain point. So I'm gonna anneal as per Bullseye's recommendations closer to the strain point. I don't quite go at 900 because spectrum is plus minus 10 degrees Fahrenheit at 890, so I do about 910. That still saves me a lot of time and allows me to anneal a thing better. See, we used to be taught that the closer you were to the annealing point when you soaked your glass to stabilize it, the better you could anneal it. But we now know that that's not true. Bullseye has shown that to be demonstrably false by their testing of annealing at 900. If I anneal from 960 to 890, that's 70 degrees. That's a long time, and it gives, to come down really slowly, it gives the glass more chance for parts of it to get out of sync thermally, that one part may be hotter than the other. But if I'm only doing it over 20 degrees, 910 to 890, then I have a much better chance of annealing it. I can actually slow down my temperature range, or temperature cooling. I can slow that down and still, so I can anneal it for longer, but actually speed up the entire process and anneal it for less hours. So I can anneal it better and still save time and energy and money. So that's important. The interesting thing over here, if you look, you'll see that the strain point is actually not where we stop this initial cooling. The strain point is there at 890, but we're gonna cool it down to 800. It's because we wanna make sure the entire thing gets down, all the glass is at the same temperature. And speaking of the same temperature, we gotta think about the annealing soak. Like I said, we used to soak at 960, we now soak at 910. It doesn't matter where you soak at, so long as it's in between the annealing point and the strain point. When you do that, you've gotta make all that glass body be the same temperature. That's the entire point of annealing, the annealing soak. The annealing soak doesn't actually anneal the glass. All it does is equalize it so that then you can anneal it. So it means that like this part over here isn't so much hotter than this, or the surface isn't much hotter than the bottom, or the other way around. Everything's the same temperature, and then you can come down slowly. After you come down to the slow cool to 800 and you've got it, that's annealed. The rest of it, if you could literally cut that kiln off at that point and the glass would be safe on the way down and wouldn't crack, the glass was going to be totally fine. Because remember, below the strain point, we can't permanently add or remove stress. We can't add any stress. But basically, in a practical terms, you cool down from 800 to room temperature twice as fast. The rate of decrease is twice as fast as it was from the annealing point through the strain point. So that's annealing and casting. I hope I got under the 15 minutes. And if there's any questions, please place them in the comments. Shoot me a direct message on Instagram or wherever you find us, in Facebook or YouTube, wherever it is that this ends up. Please feel free to hit me up, not a problem. And I want you all to stay safe, stay home, and we'll see you soon. Cheers.